Glucocorticoid-induced thermocyte apoptosis associated with endogenous endonuclease activation. To have his work published in this journal, Nature, is an accolade hoped for by any reputable scientist. The result is a publication few people read for fun. It is deadly serious. So, when we opened an edition and read, "Is the sun still shining?" we knew the article wasn't written by Flanders and Swan.
In July, the sun is hot. Is it shining? No, it's not.
No, the Nature article is certainly no joke. It seems that solar scientists have been looking for a particular kind of fundamental particle the sun is supposed to be shooting off into space as part of the reaction that produces sunlight. And they're not finding what they expect. One possibility, says Nature, is our theoretical understanding of the sun is badly wrong somehow. Another possibility, the sun has stopped shining. Well, on the face of it, it seems ridiculous, doesn't it? I mean, the sun obviously hasn't stopped shining or we'd be stone cold dead. Clearly, the theoreticians have got their sums wrong and they're casting about desperately for an excuse. But to reason like that is to underestimate the scientists' intellectual battle to understand the fantastic forces that shape our universe, the stars, the sun, the earth, life itself. The atoms that form the stuff from which everything, from the clouds and the continents to a baby's fingernail, is built, didn't come ready-made with the creation of the universe. They were forged in the nuclear furnace that lies at the heart of every shining star. The precise mechanisms by which stars have built up all the elements, from hydrogen through oxygen, carbon, iron, all the elements that go to make up you, me, and everything else, from intensely hot plasmas like these, have been worked out over the last 50 years by stellar scientists using as evidence the analysis of starlight. Naturally, the star we know most about should be the one closest to us, the sun. Go behind the sunlight, and you can see how the sun shines. It is nothing less than a vast Armageddon of hydrogen bombs that are going off all the time. Sunlight is the visible energy of all these hydrogen bombs radiating across space to our planet. Now, it is a fundamental rule in science that you get out what you put in. No more, no less. This giant balance represents the main hydrogen fusion reaction going on in the sun's interior. On this side, we put in 3 parts of the gas hydrogen. Now, these are drawn from outer space by the enormous gravitational pull of the sun, which operates not unlike a gargantuan vacuum cleaner. The result at the other side of our equation, they fuse together to produce one isotope of helium. But as you can see, this isn't enough to make the nuclear reaction start. The H-bombs haven't gone off yet. So we let the reaction produce photons, sunlight. Still no reaction? Because the energy equation, the energy balance, if you like, also demands that we produce positrons, rather like positive electrons, and they spin. We add those, and there's still no joy. And the reason lies in the spin of the positron. The energy on both sides of our equation has to balance for the nuclear furnace to ignite, and that includes that spin energy. So the reaction has also to produce neutrinos, pure elements of spin, rotating in the opposite direction from the positrons. That should cancel out the spin effect of the positrons. Add that, and shazam, the sun starts shining. That is the main nuclear reaction going on inside the sun. There are others. They produce such unlikely chemical elements as boron and beryllium, and indeed more neutrinos. That is the theory. Does the reality actually match up to that? Well, we can confirm the existence of the hydrogen. We can detect the helium. We can measure the positrons. We can bask in the sunshine. Spectroscopes show the presence of the boron and the beryllium. But what we can't find are nearly enough neutrinos. So our reaction may easily be fundamentally out of balance. So what's wrong? Is the theory incorrect? Well, the Nature article says more work needs to be done, but there are already some scientists who are trying to juggle with the theory. But of course, even if the sun has stopped generating light, there are enough photons already fighting their way slowly through the atoms of the sun's interior to bathe the Earth in sunlight for 1 million years to come. Unless, of course, the sun actually shut down its nuclear furnace 1 million years ago, and we've only just found out.
No problem. What the Irish Forestry Service is doing here is called taking first thinnings. When these trees were planted some 20 years ago, they were put down close together for their mutual protection. But now, so that they can grow even bigger, they're going to need more space and more light. And every third tree is being sacrificed. Well, chopping them down is no problem, but getting them out of the forest is not so simple. In Britain, after the trees have been sawn down, they're winched out of the rows and cut into lengths. The problem with this is that the expensive chainsaws get damaged by wet mud. But what else can you do? I mean, how could a machine possibly manoeuvre in such a small space over tree trunks and thick mud? In any case, how could a machine get the logs out? Well, there is something that can, because an inventor living in Ireland has come up with this. And with it, one man can shift up to 50 tons a day, much more than my other methods. And it can travel just about anywhere. It's basically a tractor with the front wheels removed, joined to the back half of another tractor. A drive shaft on a universal joint gives four-wheel drive, but allows the front and back wheels to work independently. Driving it, however, takes a bit of practice.
Marvellous if, instead of going off to hospital for a checkup, you could get the whole business done over the telephone. Well, now you can, using this. It's a way of having an ECG trace to check the state of your heart, done in the luxury of your own sitting room, simply by using the telephone. It can even monitor pacemakers, saving expensive ambulance trips to hospital. What you do is you hold this against your chest, you pick up the telephone, and electrical signals from the heart and pacemaker are sent down the telephone line to a receiver like this in a hospital. Now, for those of you with long memories, you may remember that in the early 70s we showed you a similar system developed in Sweden, but it wouldn't work on the British telephone system. But this one does, because in the meantime a lot of problems have been solved. A pacemaker, or ECG impulse, is so small that it hasn't the strength to go down the phone on its own. It wouldn't be picked up at the other end. So it's boosted by taking a stronger signal that looks like this and sounds like a whistle. And when you combine them, you get a signal that's loud enough to be picked up at the other end. But unfortunately, it exceeds the telephone noise limits, interfering with our automatic exchanges. In other words, if the signal's loud enough to get through, it's too loud for the system. If it's quiet enough for the system, it just won't carry the message. But this gets over the problem, and I can explain how on this oscilloscope. I'll just switch it on. Now, first of all, what it doesn't do is to try and get the message down the line by increasing the noise level. That's the height of the wave. As we explained before, that overloads the system. Instead, an acceptably low noise level is used, about there, And then the ECG information is sent down the telephone line by changing the frequency, the pitch. It's a sort of musical code. And that code is then sorted out by a silicon chip. Again, we've mentioned them rather a lot in this programme. And it's inside this receiver. So this is it, the first approved ECG and pacemaker telephone transmitter. Now, I've got someone with me in the studio, David Haverty. Hello, David, who I think it was 3 weeks ago, wasn't it?
About that, that's
had
right.
a pacemaker put into his chest because he had some problem with his heart. Now, we're going to check it out because I assume that it would be a great help to you if you could have one of these systems at home.
Certainly would, yes.
How many trips are you having to make to hospital at the moment?
So start off with once a week for 6 weeks, and then every 3 or perhaps 6 months.
So that's obviously quite a nuisance. Well, let's use the system and put it to your chest. And when you've done that, I'll pass over the telephone. And in fact, we've got the whole thing connected up by phone to a receiver in the Freeman Hospital in Newcastle. Now, on the other end of this phone is Dr. Ron Gold from Newcastle. So, Dr. Gold?
Yes.
Can you hear us clearly?
I can hear you perfectly, yes.
Good. Now, I want you to have a look at the trace on your machine. Now, Dr. Gold's got a trace just like this one, coming along here. The ECG trace is there, and the pacemaker signal is in a box in that corner. Now, what do you make of the pacemaker and the general heart condition from your receiver?
Well, I'm getting a perfect recording here in Newcastle, and from it I can see quite clearly that David's heart is responding normally to every stimulus from the pacemaker, and the figures on the right-hand side of the instrument show me that his pulse rate was 79.1 beats a minute, and it also gives me other information about the function of his pacemaker and its batteries.
So that's good news, isn't it, David?
Sounds good to me.
Are you going to be using this system?
We are at the moment evaluating this system, and we hope that it'll save some of our more distant patients, like those from Carlisle, quite a long journey to Freeman Hospital.
Good. Well, I know David would like one at home, wouldn't you? So now that we have ECGs by telephone, surely it won't be long before other checkups and diagnoses will be possible without ever leaving your home.
This is the sort of location in which any film producer is bound to get the atmosphere just right by adding the correct sound effect. See what I mean? But this is a wildlife park on the fringe of San Francisco Bay, and here, that sound has a very special significance. It's got a great deal to do with food. We humans have developed a taste for having our food brought to us on a plate. But behaviourists believe that animals do not enjoy such service. Indeed, here in captivity, they positively miss the thrill of the chase, the excitement of the game that the hunter can play as he looks for his next meal. And that's where that funny sound effect comes in. The creatures in here are Asian short-clawed river otters. Their enclosure is rigged up with a sound system which is capable of generating the cricket noise and 3 dispensing points through which actual insects can be dropped into where the otters can reach. The visitor can set the otter a challenge by choosing which of the 3 dispensing points the cricket will actually appear. Now, on hearing the sound, the otters instinctively start to look for the insects making that sound. And of course it doesn't take them long to realise that the most likely place to find them is one of the 3 dispensing points. But which one?
There's a photoelectric cell at the bottom of each cricket delivery tube. If that's the point programmed to deliver the unlucky cricket, then when the otter's paw enters the hole and breaks the light beam, the cricket dispenser is triggered. An otter lives on fish. The cricket is simply a snack to hunt or play with. And if the otter chooses the wrong hunting place, then, just as in the wild, he has to wait for his next chance.
Round the back of the otter enclosure, we can see one of the automatic cricket dispensers, looking rather like a jumbo 6-shooter. And across here is the electronic control gear, which keeps the whole sequence moving through. These counters are monitoring otter performance, how many cricket catching opportunities they've been given, how many hunting trips they've initiated on their own. The row at the bottom's interesting. That's not looking at the otters at all. That's actually monitoring the human visitor performance, observing which button the visitor prefers to press. After all, when you're into animal behaviorism, why restrict yourself to watching just the four-legged type? Interestingly, the encourage to hunt technique doesn't work equally well with all animals. Lions, for instance, are so naturally idle anyway, they only accept the slightest challenge. But in a very short time, the tigers here will be presented with, believe it or not, the opportunity to leap into the air to catch mechanically catapulted flying meatballs. And that's something the animal behaviorists will be keeping a especially close eye on.
This French device is a one-man elevator, or perhaps I should say one-woman elevator, and it's proving very useful in the construction industry and on offshore rigs, not television studios normally. You get up, you just wind these levers. It's really much easier than it looks, and it's a very exhilarating way of travelling. Coming down, though, not so sure about that. There's a braking system here, and you're supposed to just gently release the brakes. Here's Kieran.
This is the BBC Home Service. Thursday Night Theatre presents You're Nicked.
Nigel, you're home early.
Fiona, this is the last time.
Nigel, no.
Yes!
Ah!
Clump. Well, whatever you thought of the play, the sound effects were pretty good. And in the early days of radio drama, we went to enormous lengths to get realistic sound effects. But then we learnt how to record sound, and instead of a simulated farmyard, say, well, we could have the real thing. But we've never been very good at electronically creating sounds that sound real. Listen to this. Well, that synthesizer is supposed to sound like a timpani drum. But does it sound like one? Well, judge for yourself. This is what a timpani drum sounds like. But now, cock an ear to this. It's a synthesizer too. And this is what it sounds like. Well, that's almost perfect, isn't it? And the reason it can create that sound so perfectly is because it's hooked onto a computer, which has mathematically worked out the incredible complexity of the sound wave that a timpani makes. And it's stored it in its memory. And that's just the beginning. Because now that the computer knows the basic sound of a timpani, or whatever, it can change the pitch too. Listen. And even go up octaves. And that's not all. Remember those tramping feet and creaking doors? And remember, those aren't recordings. These are electronically created sounds. Well, I've got a lot more in my vast repertoire over here. Let's have a look at some of them. I've got barking, cannons, creaks, footsteps, meows, oinks, timps, dogs. Well, let's pick out one of them here. I'll go for a bark. There we are. Load it up onto the computer. Put it back in here. Now, there are some television programs which make the occasional puny attempt to get dogs to sing, but you ain't heard nothing yet. Let's see if we've got the noise first. Oh, wonderful. I thought it was wonderful. But let's take the tempo down a little now. Suppose I want to send my loved one a rather special musical greeting. Well, I can. First, let me give the computer an idea of the sound that I actually want to send. So I'll prime it again. And now I'll speak into the mic. Hello. And we have to wait a couple of seconds now for the sound wave to come up. There it is.
Hello.
Hello. Hello. Hello. Hello. Hello.
Hello, dear. Well, we're having a bit of fun with this machine tonight, but the scope it offers musicians in being able to create almost any sound you care to name is nearly limitless. But for my finale tonight, I'd like to play a little number off my latest album, a number I freely adapted from an insignificant original. And all the sounds you're about to hear were created in here. Hope you like it.
Hello.